Okay. So ABC is a triangle with orthocenter H. Oops. Yeah, sorry, Timo. I'm not an expert on inversion yet. I'm still trying to learn it a little bit, but I'm pretty sure what you were saying was correct. Okay, C is a circle through B and C. Okay, so we have the circle with diameter AH. And then we have another circle through points B and C, and it intersects that circle at X and Y. And then D is the foot of the D we've already drawn. And P is the foot of the altitude from D to XY. So I'm gonna change things around a little bit just so it looks better. Let's see. Perpendicular from D to XY. I'd like it to lie on XY if possible. Let's see if we can make it lie on XY. There we go. Yeah, let's something like that. Okay. I'm going to shrink it a little bit, but okay. And so this is point P. And we want to show that PD bisects angle BPC. Okay, so actually I'm already seeing something fairly quickly. Basically, if we extend XY to meet BC at a point, so yeah, let me just change things around a little bit. Oh, it looks like, yeah, okay. So basically B, C, D and that point are in we have to show they're in harmonic conjugation. Okay, so I'm going to draw this point here, G. We want to show that B, C, D, and G are in harmonic conjugation. That would solve the problem. X, E, F, Y, X, Y, F, E, and B, C are concurrent by the radical axis theorem. So I think we might have already solved it actually. So this was actually a fast one. Okay. So from what Timo said, the radical axis theorem says that X, Y, F, E, and B, C are concurrent. And then that means that since basically if we know that, then we know that B, C, D, and G are in harmonic conjugation because A, D, B, E, and C, F are concurrent at H. And so from there, the problem follows. So I'm sorry, that was a little fast, but yeah, that was a fast proof. So in fact, I think we might have actually, I don't know if I3435 is left yet, but yeah, we solved this one. So just for Rom, so Rom, do you know the idea if AD, BE, and CF are concurrent, then B, C, D, and G are in harmonic conjugation? Have you seen that theorem? That's
Yeah, I've seen it somewhere.
Yeah. So basically, B, C, D, and G are in harmonic conjugation. And then, if that's true, whenever you have B, C, D, and G in harmonic conjugation, if angle GPD is 90 degrees, then that means PD is the angle bisector of BPC. So that's like the second video on my channel on projective geometry. Does that look familiar at all?
Yeah.
Yeah. So I'm not going to write it all out, but basically that solves the problem. So I'm going to move to another.
Sorry, but I think could you explain why this is 90 degree again? I was just a little uh,
Oh,
distracted.
it's okay. So angle GPD is 90 degrees because P is the foot of the altitude from D to XY.
Okay.
So since P is the perpendicular from D to XY, angle GPD is 90 degrees.
But why is it perpendicular?
Oh, why is DP perpendicular to XY?
Yes.
Oh, that's given in the problem statement. It says, furthermore, let P.
Oh, so bad of me. I'm sorry.
It's all good, no problem. So since angle GPD is 90 degrees, because those 4 points are in harmonic conjugation, B, C, D, and G, there's a property that says that means that PD is the angle bisector of BPC. And so that solves it. So yeah, we can chat a little bit more about it on Discord, but it's two very useful theorems. So I'm going to move on to the next problem. This one looked kind of fun. So I just looked at it very briefly, but didn't really work on it very far. So we have a triangle ABC where angle C is 90 degrees. So I'm going to switch B and C here. Okay, so angle C is 90. E is an arbitrary point on AC. F is the midpoint of CE. All right. G is the midpoint of BC. Whoops. H is the perpendicular from C to AB. I'm so bad at this. O is the circumcenter of AEH. And then we want to show that triangle OGF is similar to triangle ABC. All right. Let's make the diagram a little bigger. All right, so FG, since F is the midpoint of CE and G is the midpoint of BC, FG is parallel to BE. Let's see. Oh, let me try some stuff. Yeah, okay. Sorry, I'll be right back. Just 1 second. All right, so let's see what we have. Okay, so I'm trying to see if I can prove angle OFG is 90 degrees. Maybe I could use the gliding principle somehow. Yeah, I'm kind of liking the gliding principle a little bit. Let's see. Okay, let me try this. So if I draw a perpendicular from E to CH at D, triangle EDC is similar to triangle CHB. EDC. So that's not hard to show by angle tracing. So then we can apply the gliding principle. So E corresponds to C in those two triangles. B corresponds to H, and C corresponds to B. So if I take the midpoint of the three corresponding segments, so I'm going to take the midpoint of DH. It looks like it lies on OG. Is that always true? That is always true. So I could try to prove that. But if we take the midpoint of DH by the gliding principle, both are similar to triangle EIG. Okay. So I'm sorry, FIG. So have you guys seen the gliding principle before?
Yes, it's reflection of transition.
Okay. But I don't know yet that OI and if I have to show that OI and G are collinear. We don't know that. Let me hide this. How do we prove that? So I'm going to draw in that. HO. So let's see, what I'm going to do here, I'm going to take the midpoint of EH. So we know JI is parallel to D. Yeah, I want to show that OI and G are collinear. Let me try something. I don't do anything. Okay, let me see. Let me try something. No. Yeah, how do we use that O is the orthocenter, or O is the circumcenter?
OJ perpendicular to EH.
So, or OJ is perpendicular to EH. Yeah, so that's one condition. So OJ is parallel to IG. Okay, so I think, yeah, if we can show that angle OJI, or hold on one sec. Okay, so let me just try something. Yeah. For ED and I don't think ED and G are collinear. Let's check it. I'm not sure if this fact is useful. It looks interesting. Well, this fact, it means that angle FGI. So we know that in triangle OGF, we know at least one of the three angles is equal to triangle ABC, because we know that we know that FGI is equal to one of the same angles, and if we can show GI and O are collinear, that would get us there. Yeah, so what does that mean if GI and O are collinear? So I'm thinking GO is like the line connecting the centers of two circles. So basically, if you have the circumcircle of AH and the center's O, and then you have this circle through CHD, and the center is G, then the line connecting the two centers should be perpendicular to the radical axis. So, and it looks like these three are concurrent. I don't see why right now that is, but that's what it looks like from the diagram. Let's see. It could be obvious, and I'm just not seeing it, but okay, so if we assume that those three concur here, then OG is perpendicular to KH. So we want to show that OI is also perpendicular to KH. Okay, actually, I see why these three are concurrent at point K. So, so basically, if I hide EB for a second, we have so EK and B are collinear. So that just proves okay. Okay, so basically what I was saying is since OG has to be perpendicular to KH, since O and G are centers of those circles, and if you take the line between the two centers, it's perpendicular to the line connecting the intersection points. Does that make sense?
Yes, it will also bisect.
Yeah, and it also bisects it. Yeah. So OG is the perpendicular bisector of KH. All right. Then if we can show that like GI is also the perpendicular bisector, then that would mean that like OI and G are collinear. That makes sense. I kind of have, so since AHI is a right angle, AO and I are collinear.
Can you repeat again?
Sure, I'm going to type it up in a sec. So since angle AHI is 90 degrees, points AO and I are collinear. Does that make sense? Basically, AI is a diameter, since angle AHI is 90 degrees.
Yes.
Okay. So if we can show that AO and G are collinear, that would help us. And that we can do by an angle chase. Okay, so I think I've got this here. HKD HI equals KI. So angle HKD, we can show that's 90. Oh yeah, I agree. I have a different, so I'm sure there's a way to get that to work, what Timo just said. But I'm gonna write out, I'm not sure what it is right now, but I'm gonna write the idea I have in mind. Okay, so actually, let me go back to Timo's idea. Hold on a sec. HKD is 90. Yeah, I'm not sure. There might be a way to do that. I'm just not sure right away what it is. But I'm showing if I can show that if I can show that A, O, and G are collinear, then I have that would solve the problem. And that looks like it shouldn't be that hard, right? To show that A, O, and G are collinear.
Yeah, I think
they're
AOG are not necessarily collinear as well uh, because the circumcenter of triangle ABC and triangle AEH they don't necessarily have to be collinear with like line AOG which you are claiming to be collinear it also has to pass through circumcenter of ABC.
Yeah, I know you're right. This fact right here is wrong. AO and I are not necessarily collinear because well actually wait, why aren't they? I'm trying to. Okay, now I'm really confused. Whoops.
Is the G is the midpoint of it, and since G is the midpoint and ABC is circumcenter and like the line through A and circumcenter of triangle ABC will also have to pass through O, and that doesn't necessarily passes through G. Because if you extend AO, it will always intersect with circumcenter of triangle ABC.
Yeah, no, I see what you're saying. Like G is kind of like, in other words, we can move E, but G is fixed. So it couldn't be that AO and G are collinear. Right. That's basically what you're saying, right? Like G, like if we move E around, G stays in the same place, but O changes. So it can't be that AO and G are collinear, right?
Yes,
Yeah.
that is also a approach.
Oh, I'm sorry, you were thinking of it a different way. But
No, I'm saying that if you extend AO, it will always meet the circumcenter of ABC because uh,
it'll
it,
pass
it
this.
always passes through circumcenter of ABC.
Uh,
As uh, does that make sense?
I I think so. You're saying it'll always pass through the circle. Well,
Circumcenter of ABC.
well ABC is a right triangle, right? So the circumcenter is going to be the midpoint of AB, right?
No, no, that is completely different. It doesn't have to be right angle triangle. The fact that A is a common vertex of both of the triangle. Okay, wait a second. I'm confused even now. But one thing is sure. AOG. I don't think it. A like AOG is doesn't look to be
No, they can't be
collinear
collinear
because.
because if we like move, we can make point O really high. Yeah, there's no way AO and G can be collinear. That was a mistake I made. But let's see. So Timo is trying to show that angle HKD is 90 degrees. Yeah, that's interesting.
KD not be 90 degree because angle D is already 90.
Angle HKD. I'm sorry.
Angle HKD can't be 90. No, no, it can be.
Let's see if Timo has an idea. We can try to show OG is parallel to KD. That's interesting. Yeah, that's exactly what I was trying. So OG is the perpendicular bisector of KH. Yeah, let's see. And what's also interesting is OF is the perpendicular bisector of EK. So I wonder if that helps us. See. Is Fi the perpendicular bisector of KD? It looks kind of like it. I mean, let's see, that would mean, I think so. Okay. So F is the circumcenter of EDC. We want to see does K also lie on that. And I think we might be able to just do that with an angle chase. Yeah, I think we can use an angle chase to show that. Angle CKE is 90. Yeah. So yeah, Timo is saying, yeah, so let's see, angle CKE is 90 degrees. And so yeah, that basically says that, okay, so I'm gonna draw this. Okay, so CDKE is cyclic. Okay. With circumcenter F. All right. And so if that's true, let me go back to what Timo was saying. See, Timo. So Timo was saying, okay, yeah, Fi is the perpendicular bisector of KD. And we already know that Fi is perpendicular to IG. I think we're almost there. Let's see. So you can show, okay, I can show KD is parallel to IG, but I want to show KD is parallel to OG. Is that obvious? Yeah. Basically, I want to show angle DK. I want to show angle DKH is 90 degrees. But that's true. Okay. Yeah, I think we're there. Yeah, we have enough information to finish it. So, okay. So, Let me just think about how to write this for one second. Well, actually, do we know that KH is parallel to FI? If I could show that, that would solve it. I feel like I'm going in circles here. Yeah, we do know that. So I'm getting so confused here.
Emo says HI equals to KI. So can we apply that?
How do you know HI is equal to KI? I know that HI is equal to DI.
Yes, if we prove that HI equals to KI equals to DI, it will ultimately solve the problem.
Yeah, if we can show HI equals KI, that would solve it. We know HI is equal to DI, but I'm not sure exactly how to proceed. I wonder if we could do an angle chase to show that angle HKD is 90 degrees. So HKD, it's like 360 minus EKH minus EKD. And that is, yeah, okay, no, we got this. Okay, it's just an angle chase. So,
It's just angles.
yeah. Yeah, I was making this a little harder. Let me break up the statement just so. I'm trying to break it up into different lines. Let's see if this works. Whoops. I'm not 100% sure this will work, but let's see. What? That's not what I wanted. I just want to break up this equation into more than one line. Let's try this. All right, we got it. Okay, so once we know that angle HKD is 90 degrees, we're basically there because okay, so we know that angle FIG is equal to 90 from the similarity. We have angle FIG equals 90. Um, I know we're there. I'm just thinking how to. Okay, so I mean that means IH equals ID equals IK, right? Since angle HKD is 90 and I is the midpoint, we know that IH equals ID equals IK. And so that means that OI is the perpendicular bisector of KH also. And so that means that OI and G are collinear, because if OI is the perpendicular bisector and OG is also the perpendicular bisector, we have OI and G are collinear. Okay. And then I feel like can we finish it off? Yeah, I think we should be able to finish it with an angle chase. Let's see, Timo. Yeah, OF is the bisector. Okay, so EK is parallel to FG. So angle OFG is 90 degrees. Okay, so I mean that shows that angle OFG is 90 degrees. Okay, and yeah, so since OIG, that solves the problem, because if OI and G are collinear, and we also have okay, so OF has to be perpendicular to EK because that's the line joining the two centers. So it's also perpendicular to FG. So if OF is perpendicular to FG and OI and G are collinear, then since we knew FIG was similar to ABC, then OFG, it's easy. It's a fairly easy calculation to see that that also has to be similar. So and that solves the problem. All right. And that should be it. So any other questions on that? Does that make sense? All right.
Yeah, the collinear part was good.
Yeah, once we know OI and G are collinear, yeah, that was key.
Yeah, it's done.
All right, so I am going to move on to the next problem. This one looks kind of hard, actually. I'm kind of in the mood for an easier one. Let's see. This one looks like it should be easy. Let's try this one. We get build some confidence. But I can't see How do I maximize the figure? There should be like a thing that lets me maximize it. Ah. Yeah. It won't let me maximize the screen. Let's just do this. Okay. All right. So triangle ABC has incenter I. I could have just used the incenter thing that I 1 3 4 3 5 said, but I'm gonna be lazy. So okay. So E is on BI. It's on the ray BI, so it could be past I. The circumcircle of AIC intersects CI at P, or AIE. Intersects CI at P. Show the orthocenter of PIE lies on BC. Is that true? Let's see. Yeah, yeah, it looks true. Interesting. Okay. How do we show that? It seems so random. But yeah, E can be past point I. Yeah, I didn't let it work in this figure, but yeah, I'd assume the proof would be the same in that case. How do we do this? So the reflection of the orthocenter over the side. So basically, if we drop a perpendicular from E to PI, so those three are concurrent. Is that obvious? So the perpendicular from E to PI looks like it passes through this intersection point. And I think we can prove that using an angle chase. So, okay, so I'm going to label this intersection point D. And then I want to show that angle EDI is 90 minus angle DIP. Okay. So EDI is EPI. Let's see. For EDI is EAI. I'm just sort of doing an angle chase in my head here. Let's see where I can go with this. So let me move this away a little bit. So think this might be a start. See what this does. I'm going to show DIP is 90 minus IDE.
Should we drop the perpendicular from P to BC, then try proving that the line joining their two point of intersection is perpendicular to PE?
Do you say the perpendicular from P to BC?
Yes.
Let's see.
No, sorry, I'm mistaken. Sorry.
That's all right. I think I have an idea. Hold on just a sec. So DIP is this. IDE let's just keep it like this. I feel like it. Whoops. What just happened there? Basically, we want to show these two angles add up to 90, right? If DIP and IDE add up to 90, let's see, AEI, IAE. Yeah, so I have that it's true. This might be a messier angle chase than I need, but and then it should be easy to show that that's equal to 90. Let's see. Yeah, it is. I'm just going to say this equals 90 by an angle chase. I'm sure there's an easier way to do this, but it looks like there should be a way to get, because angle DCI is half of angle C, right? And angle AIE is like 180 minus half angle A minus half angle B. So yeah, if you work out the algebra, this should equal 90. And so that means DE is perpendicular to IP. Okay. Let me move things around a little bit. Okay. So what did we want to show? We want to show the orthocenter PIE lies on BC. So okay, so yeah, that solves the problem because basically the orthocenter is the unique point on the altitude from E, such that when you reflect it over PI, it lies on the circumcircle. But that's true because if we take this point, like you call it F, right? How do I hide it? So basically, since CI is an angle bisector and CP, okay. So let me write it this way. So okay, so implies I'm gonna, so that means that the reflection of D over PI, or is D. And so that means that F is the orthocenter of triangle PIE. Does that make sense? So basically, one way to characterize the orthocenter, it's the unique point on a given altitude, so that when you reflect it over the side, it lies on the circumcircle. So I brought that up on my channel a couple times, but basically, F, it's on the altitude from E to PI, and when you reflect it over PI, it lies on the circumcircle of triangle PIE. So that's one characterization of the orthocenter. There's a little bit to do to prove it, but it's not that big of a proof. But have you guys seen that before?
Oh, yes.
No, looking forward to.
Um,
Could you explain that thing again? So, yeah, it completely went off head.
yeah, absolutely. So I'm going to erase this just for a sec, just to explain the idea. So actually, no, I'm not going to erase it. I'm just going to move it to the side. So if I have a triangle ABC in general, whoops, it doesn't matter what the letters are, but I'm going to draw the orthocenter. Okay, and now I'm going to draw the circumcircle. So if you take the orthocenter and you reflect it over any of the sides, it lies on the circumcircle. So that's a fact. If you haven't seen it, I'd recommend proving it. But basically, if
Yes. I have proved it couple of times, but I couldn't recall. Yes, thank you.
Yeah, so basically I'm using that idea, and the converse is kind of also true. So if L is on the perpendicular, and it's true that you reflect K, if you reflect K over BC, you get L. But like,
Yeah.
basically the converse is kind of true is what I'm saying. So the orthocenter, it's the point on an altitude so that when you reflect it, it lies on the circumcircle. You see what I'm saying?
Yes, I knew this thing, but while you said, I couldn't imagine at that same point.
Yeah, it's kind of hard to see when you have like an obtuse triangle like this, because the orthocenter is like
Yes,
outside of the
yes.
triangle, right? Um,
Yes, you don't regularly get to see this property in obtuse angle triangle. I mean, not factually, but you don't see it in books, and also you don't. You always have that acute angle in your head.
yeah. Um, but yeah, it just happened to work out for this problem. So yeah, it's pretty convenient. All right. I think, let me see. This might be a good place to stop. This is a problem I've already done before. I just sort of had it in my back pocket. This is what we just did. This one looks a little tricky. Do you guys think here's a good place to stop? What do you guys think? Do you want to do more or you want to stop?
As you wish.
Maybe one.
Channels here.
All right. Let's see. Oh, this one Rom showed me before, actually. Uh, but I think the only one we haven't done is this. Let's see if it's quick. Um, okay, so we have a quadrilateral ABCD. And we draw the centroids of all the possible triangles. So kind of what that means is, let's see. Did I miss a segment? Yeah. Or now I'm just confused. Okay. So the centroid of ABC is P. The centroid of BCD is Q. The centroid of ACD is R. And the centroid of ABB is S. So we want to show that PB, QA, we want to show that those four segments are concurrent. This is a messy figure, but let's see. PD, QA, RB, and CS. Yeah. So messy figure, but basically we want to show that they all concur at this point. I wonder if there's a way I can make the figure a little bit cleaner. I think I might have an idea. So
I think we don't need to prove all the lines are collinear, because if we prove like 2 to 3 lines are means concurrent, then other lines will be also concurrent.
yeah, so yeah, you're pointing at, yeah, we don't need to show all four. We could just show three, and then by the same argument, the others would be true.
And again, the figure is quite symmetrical. So if you are able to work on only one side of the figure, like there are four perspectives of like we could hunt for P or Q or R or S. So if we try to concentrate on one side of it, then it is quite easy because the figure is complicated. So they don't. I
Yeah,
think we should start with.
you know what idea I have? What we could do is, so P is the centroid of ABC, right? So it lies on the median BI, and it's 2/3 of the way from B to I. Let's see what Timo. QP is parallel to AD. Let me think about that. It's probably obvious, but I'm trying to see why it's true. Oh yeah, that's true because yeah, I see what Timo's saying. So Timo is saying basically, so P is 2/3 of the way from A to F, right? And Q is 2/3 of the way from B to from B to F, right?
Parallel.
Yeah. So QP has to be parallel to AD.
Yeah, similar triangles.
So I'm going to write that out.
And yes, yes, I like I said, the symmetry holds for all of them. So um, like SR parallel to BC and AB parallel to uh, QR. Yes, it all comes aligned.
Yeah. So Q, and then like you said, we have all the symmetries. So Timo keeps beating me here. QP is parallel to AD, and so we know in which ratio these lines intersect. So so we know like what ratio PD cuts AQ into. I'm trying to formalize this. So okay, so first of all, they're all parallel to the sides, right? So PQ, each one's parallel to the opposite side.
And the figure is similar, like ABCD is similar to PQRS.
So I can see that they have the same angles. So when two
No,
triangles have the
their
same angles,
sides are also proportionate.
yeah, the
Because
sides are also proportional because they're in the same ratio to the original figure. Yeah. So yeah, so the sides of PQRS are parallel to those of ABCD and in the same ratio, and I'll just say and proportional. So the PQRS has to be similar to ABCD. All right. And once we know that, Timo said we should be finished. I'm trying to see why that's true. So I know, like, we know the ratio that AQ cuts PD into. I can see some of it. He said we know the ratios that they all cut the other ones into, and so that proves it. I'm trying to see exactly how you would show that. So this is an interesting. So this, I wonder if, yeah, it looks like EG and FH also concur at that same point. So basically, if we can show, so Timo says it's clear. I'm trying to see why. All right. Is it, or Ram, is it clear to you why they'd have to concur? I don't totally see it yet.
I have not seen also.
Okay. Okay, so PD intersects AQ at T. Okay, so I'm going to hide these things for now. T. And BR intersects AQ at T prime. Ah, okay. So it cuts. Okay, so BR and BP cut AQ in the same ratio. And we can find that ratio using Menelaus. Okay, so I'm going to write this. This drives me crazy. So I'm just going to move it up here for a second, and then I'm going to move it back. So okay, this drives me crazy. But so I'm thinking about using Menelaus. Let's see. Yeah. So, oops, didn't want to do that.
Timo says that the ratio is 1/4.
All right. So by Menelaus, dq over df times fp over pa times, was that what I wanted? I wanted to see what ratio dp cuts a, yeah, okay. And then if you do the algebra, then AT over TQ is 4. And then similarly, I'll just say similarly, BR cuts AQ in a 4-to-1 ratio. So BR, DP, and AQ are concurrent. Okay. And then by the same argument, yeah, so yeah, I'm just writing it out just to, but by the same argument, BRDP and CS are concurrent, and that solves the problem. All right. Let me see. I'm just stretching it out here. So we've done all these. Here's an easy one if you guys want, but
But
Menelaus
I
isn't
want to
necessary.
ask Timo how without Menelaus theorem he could prove. Like, write it in small 1 or 2 words in chat, because
He
I was also seeing it without Menelaus theorem, and
Yeah, he says we don't need to. So let's see. So AD over PQ. So AD over P, or I'm sure he means AD over PQ is 3. Yeah, 3. So somehow he's using similar triangles, I guess. Let's see.
yes, no Menelaus is required because
I think I see what he's, yeah, I see what he's saying. So basically triangle PPQ is similar to triangle ATD. So if you use those two similar triangles and you know that AD is 3 times PQ, then you know that
yes, because we
PP,
know the ratio between AP and PF, so we can also find the ratio between PQ and AB, which will result in 80 by TQ.
yeah. Now wouldn't this be, wouldn't the ratio be a third then, AT over TQ? I'm sorry, wouldn't it be 3 and not 4? Yeah, I think it would be. So I think, but yeah, the yeah, so I think he says in his comment, yeah. So this is 3. But yeah, he did it without using Menelaus. You don't have to use Menelaus because you can just use. I'll just type it. DAT to show that yeah. So you don't need Menelaus. There's no need to use it. All right.